Hi guys, in today's video we will see how to simulate an integrated oscillator ramp like this. To simulate this on LTSPICE we have to understand how it does work first on the schematic. And as you can see here we have a mirror load, mirror current, PMP mirror current. It is a PMP because on this side here you have the power supply. And then you use another PNP transistor to supply the capacitor. So the capacitor will start to charge because we assume that at time t, this is V of C, start from 0. He will start to charge, and at a certain point it will ramp up to a slope which is dependent to RC. Now, once it reaches the desired voltage, which here there will be a reference, this will activate a comparator, and the comparator will activate the logic to reset the ramp. He will activate a current source of 12 milliamps, but you can do also in some other ways to decide the slope of this second phase. So the first phase is the first phase of this oscillator is decided by the RC here, and the other phase, the T off, is decided basically by the discharge current of 12 milliamps. You can even put if you put a very high current like 1 amp, you can even have something like this. A ramp like this is especially useful when you have to, for instance, generate auxiliary ramp for current control. So we will do this instead of this. So let's open LTSPICE and let's see how we can simulate this guy. We first want to put the voltage, which will be set to 5 volts. And then we want to design the PMP pair like it is reported on the schematic. Like this. Now let's select the first of the list. And let's use another PMP here. Now this guy here has to supply a capacitive load, which we will call V of C. It is important that you have to write that this node starts from 0, otherwise it won't work. It will start already charged, so equal to 0. And we don't want that. So now, the discharge path, so the charge path, has also to follow the resistor R, which will be put to, I don't know, 1 kilo. And this to 50 nano to start. Now we need to design the discharge logic. To design the discharge logic, okay, first let's see if in 1 milli this guy charges. Okay, so it does charge. Ah, sorry. This is not, sorry, it was like this, because it is a mirror current. Okay, so it is charging. Now we need to design the logic so that when it reaches a certain voltage, it will create a ramp. So we need to design a comparator, and we need also to imagine that this guy is inside an integrator. So it is an IC circuit. So we can only allow ourselves to use one op amp just because we want to make the things faster. But in reality, you can't, I don't know, put the voltage here to 3 volts. You can't because you are in IC circuit. So you have to reason. Your reasonment should be of course, compatible with an integrated circuit. So to generate the reference design of this comparator, we need to generate a reference circuit. The easiest and stable way that I know is to put two MOSFET like this. The first is to ground and is connected to the voltage to the reference voltage. The other instead is shorted in the diode connection like this. This will generate a stable voltage referator also in temperature. Let's check with the simulation, and the voltage is set to 1.6. This is also called VTH voltage reference, and it is a very good. It is a simple and also very good circuit because it is very stable with the temperature. So let me draw a rectangle here. So this is a current PNP current source, and this is VTH reference voltage. So now the circuit is more realistic because we are just using op-amps and MOSFETs. We need to take the positive voltage of this guy here, and then we say when the positive voltage is higher than the threshold voltage, which is this, we have to reset this guy here. So we can either put a switch with a current source, or we can either put another MOSFET. I'd rather say that in this case, just for simulation purposes, just put another MOSFET and design a feedback network like this. So this comparator will drive a MOSFET, and this will reset the voltage V of C. Like this. Now, I know that it is not exactly the circuit like this because the guy put 10 milliamps, 12 milliamps, which describes the slope of the turn-off phase. Now, let's run the simulation again and let's see what is going on. As we expected, at each off period, the MOSFET will drain almost 1 amp. So in our case, the ramp generated, wow, works nicely. It has a turn-off period which basically is in the order of picoseconds. So we generated a Sawtooth instead of a triangular waveform, but I don't care. So let's call this integrated IC Sawtooth generator. The advantage of this guy here is that since it is done with just MOSFET and PNP logic, it can go very fast without worrying about the slew rate. So let's see. How much frequency is this? I think that 30 kilohertz. I think that the formula should be more or less equal to this. The oscillation frequency is equal to 2.2 over RC, meaning that if I put 300 ohms, I should increase safely the switching frequency, like I'm doing right now. So now I have 100 kilohertz, so R equal to 300 and C equal to 50 nano gives F equal to 100 kilohertz. Now the CTC converter go even beyond in frequency like 250 kilohertz. So we wanted to reach a combination that allows us to use this kind of frequency. an higher frequency. I'd say that 20 nano should be enough. Let me let me uh, let me see. Yes, more or less we reached what we wanted. So the user basically can just design the resistor and the capacitor here to select the appropriate oscillation that he desired, to select the appropriate switching frequency that he desires. So I think that we can close the video now, and because the ramp is designed, and this is how you design, for instance, IC circuit, because in IC circuit you need always to put current sources in a transistor and to generate also reference voltage like this. Now the op-amp should be done with transistor as well, but let's skip that part because it is just a stage that you just check on Google how to design a transistor with op-amps, and there you have it. But the circuit is works just fine like this. So let's call this file IC Sawtooth, and thank you guys for your attention, and I will see you on the next video.